Usually, when we talk about a time machine, there is this expectation of something straight out of science fiction.
Right, yeah. Like a DeLorean or something.
Exactly. A DeLorean with all the glowing circuits, or some massive spinning metal ring generating a wormhole in some secret underground lab.
Hmm.
I mean, time travel is supposed to be this fundamental violation of the laws of physics.
It always feels like it has to be some impossible manipulation of reality, you know? We're so conditioned to think of time travel as breaking the rules of the universe.
Right. But stepping into the world of astronomy and astrophysics, you realize we actually have a functioning time machine right now. And it doesn't break the rules of physics.
No, it relies on them completely.
It really does. So welcome to today's deep dive. Today, we are looking through a massive stack of sources. We've got detailed engineering schematics for a spacecraft. We have mission logs from this just intensely complicated deployment phase, and several recent research papers detailing the early scientific findings.
It's a lot of material to go through.
It is, yeah.
Yeah.
But our mission with this deep dive is to understand the beautifully clever design choices that allow the James Webb Space Telescope to literally see the very dawn of the universe. We want to take you on this warm, unhurried journey to break down the complex science here.
And to set the stage for how this instrument operates, I mean, we really have to look at what it was built to do. So the James Webb Space Telescope, which astronomers often just call JWST.
Or just Webb, right?
Yeah, exactly, just Webb. It's the successor to the famous Hubble Space Telescope.
Which we all know and love.
Right. Hubble spent 30 years showing us the cosmos in unprecedented detail. So when they were planning the next generational leap, the ambition had to be monumental. The goal was to build an instrument that could see further away than anything before it.
And physically, seeing further out into space inherently means seeing further back in time, right?
Yeah.
All the way toward the first stars and galaxies that ever ignited.
Exactly.
But let's unpack the mechanics of that immediately, because it's so wild. How exactly does looking further out into space equate to looking into the past?
Well, it all comes down to a really foundational physical rule, which is that light takes time to travel.
Right.
Even though light is the fastest thing in the universe, moving at, nearly 300,000 kilometers per second, it is not instantaneous.
Okay, so it has a speed limit.
Yes, exactly. So when you look at the moon, for example, you aren't seeing it as it is this exact second. You are seeing it as it was a little over a second ago.
Because that's how long the light took to bounce off the lunar surface and cross that distance to your eyes.
Right. And the sun is about 8 light minutes away. So you see it as it was 8 minutes in the past.
Wow, okay. So the further away an object is, the longer that light has literally been in transit.
Correct. If a galaxy is, say, 1 billion light years away from our solar system, the light entering a telescope's lens right now left that galaxy 1 billion years ago. We are capturing a snapshot of the deep past.
That is just incredible to think about.
It really is. But here is the central challenge of this whole mission. To see the absolute deepest past, like the very beginning of everything, James Webb had to be built with one very strange, almost counterintuitive quirk.
Okay, what is it?
To see the oldest light, it doesn't use visible light at all.
Wait, really? We spent decades and billions of dollars building the most powerful telescope in human history, and we purposely designed it so it can't see what our human eyes see.
Yeah, pretty much. And that's because the universe simply won't allow us to use visible light for this. It comes down to a cosmological mechanism called redshift.
Redshift. Okay, let's break that down for someone who maybe doesn't have a huge science background.
Sure. So we know that the universe isn't static, right? Space itself is actively expanding. It's stretching out in all directions. And as it stretches, it carries all those distant galaxies away from us.
Okay, but let me challenge that for a second, because this is where cosmology can get kind of tricky.
Yeah.
If the universe is expanding, how do we know the light is physically stretching out? Couldn't the light just be, I don't know, losing energy over a 13 billion year journey? And that's why it looks different to our sensors.
That is a really logical question. And honestly, for a long time, early physicists debated exactly that. They called it the tired light hypothesis.
Tired light, I love that.
Yeah, but we know now that the light isn't just losing energy or getting tired. We observe that the entire spectrum of light from distant galaxies shifts uniformly in a way that exactly matches the mathematics of expanding space.
Oh, I see.
Yeah, the fabric of space itself is the medium that is expanding, and the light wave is just embedded in that fabric.
Okay, so think of it like taking a deflated balloon and drawing a tight squiggly wave on it with a marker. As you blow that balloon up, the rubber itself stretches.
Yes, perfect analogy.
So that tight squiggly line gets pulled wider and wider. The peaks and valleys of the wave physically spread apart from one another.
That is an excellent way to visualize the mechanics, yeah. Because light travels in waves, as the physical space stretches, the light waves get stretched out too.
Makes sense.
So when a light wave's peaks spread apart, its wavelength becomes longer. And in the spectrum of visible light, the colors we can actually see, the longest wavelengths are red.
Right.
So as the light from the early universe gets stretched over billions of years of transit, it shifts toward the red end of the spectrum. Hence the name redshift.
But the stretching doesn't just stop at red, right? It keeps going.
It does. Light that originated from the earliest galaxies as ordinary visible light, or even ultraviolet light, has been stretched so much over its massive journey that by the time it reaches our solar system, it has fallen completely off the visible spectrum.
Wow.
Its wavelength is now longer than red light. It has actually become infrared light.
Infrared, okay.
Yeah, and we can't see infrared with our eyes, but we interact with it every single day.
Huh.
It is the exact same sort of light that the human body gives off as warmth.
So if you want to see the ancient universe, visible light is practically useless because it's simply not visible anymore. It's been stretched out of existence as far as our optical sensors are concerned.
Exactly.
It's kind of like an everyday analogy would be like a siren dropping in pitch as an ambulance speeds away from you down the street.
Yeah.
But instead of sound waves stretching out and dropping in pitch, this is applied to the pitch of light waves.
That's a great way to put it. The pitch of the light is dropping into the infrared, so it forces the engineering hand. You absolutely must build an infrared telescope.
Right. But reading through these mission logs, it looks like picking infrared kind of accidentally solved a massive, completely different problem that astronomers were dealing with, something about space dust.
Oh, yes, it did. Infrared has this profound second superpower, basically. It slips right through thick clouds of cosmic gas and dust.
Oh, really? How does that work?
Well, in the universe, new stars are born inside incredibly dense nebulas. To visible light, those dust clouds act like thick concrete walls. A visible light telescope like Hubble can only photograph the opaque outside of the cloud, but because infrared light has a much longer wavelength, it just glides right past those small dust particles.
Oh, I love that. So by designing Webb to look back into the deep past, engineers inadvertently gave it the ability to peer into stellar nurseries happening right now. It can see through the dust to watch brand new stars and planets being born in real time.
Yeah, it basically opened two entirely different doors into the cosmos with one single engineering choice.
That is just brilliant. But transitioning a space telescope to rely on infrared has to create a massive mechanical issue, right? Because, like you said, infrared light is fundamentally tied to heat radiation.
It is.
So anything that is warm is actively glowing in the infrared spectrum.
Precisely, and that includes the telescope itself.
Right. If the metal frame or the onboard computers or the scientific instruments are even slightly warm, they emit their own infrared radiation.
And you have to remember, the entire purpose of this machine is to catch the faintest imaginable whispers of ancient heat arriving from the edge of the observable universe.
So if the telescope is warm, it would be like trying to photograph a single glowing candle while you were standing inside a roaring bonfire.
Exactly. The local glare from your own heat completely ruins the exposure. It drowns out everything else.
So how do you solve the bonfire problem?
To solve it, Webb has to operate in a state of staggeringly deep freeze. We're talking hundreds of degrees below zero. It cannot emit its own heat, otherwise it just blinds its own sensors.
Wow. But, if you're listening and wondering why we didn't just tuck the telescopes into low Earth orbit and let it hide in the Earth's shadow to keep it cold, it comes down to planetary heat, doesn't it?
It does. The Earth is massive, and it emits and reflects a tremendous amount of thermal radiation.
Right. Our planet is basically a giant space heater.
Yeah. You simply cannot park a sensitive infrared instrument that close to our planet. It would bake.
So Webb had to be sent far away from the bonfire.
Very far away. It operates roughly 1.5 million kilometers away from Earth.
1.5 million kilometers. Just to put that in perspective for you, that is roughly 4 times further out than the moon.
Exactly. But it doesn't just float out there randomly, It's parked at a very specific gravitational location called the L2 Lagrange point.
Okay, let's break down the physics of L2, because reading about this, it is just a brilliant piece of orbital mechanics. Why pick that specific spot?
Well, normally, if you put an object in orbit around the sun at a distance of 1.5 million kilometers further out than Earth, It would take longer to complete an orbit than the Earth does.
There's a wider track to run.
Right. It would move slower, and eventually it would just drift away from us.
Okay.
But L2 is this incredible gravitational sweet spot. At that exact distance, the combined gravitational pull of both the Sun and the Earth provides just enough extra inward tug to increase the centripetal force on the telescope.
Centripetal force being the inward force needed to keep an object moving in a circular path.
Right, exactly. So because of that extra gravitational tug from Earth and the Sun working together, Webb can orbit the Sun at the exact same speed that the Earth does, despite being further away.
Oh, wow.
Yeah, it stays perfectly locked in pace with us.
It effectively stays in our pocket as we both travel around the Sun.
It really does.
And that orbital lock is what completely solves the heat problem through pure geometry. Because from the perspective of L2, the Sun, the Earth, and the Moon all lie in roughly the exact same direction in the sky.
Which is the clever alignment that makes this whole thing possible. It means you only need one shield to blank all three sources of heat at once.
That is so smart.
Webb carries the sunshield roughly the size of a tennis court, constructed of incredibly thin, highly reflective layers. It faces that shield toward the Sun, Earth, and Moon.
And it just blocks the heat.
Yep. The shield absorbs and deflects the heat, while the telescope itself faces permanently out into the freezing void of deep space. It operates in absolute frigid darkness.
So the telescope is literally shivering in the dark, perfectly shielded from the heat of our solar system. But, I mean, it still has to physically gather those faint, stretched-out light waves. And to catch incredibly faint light, you need a giant mirror.
You do?
I like to think of it like a massive acoustic dish you might use to capture a faint whisper across a crowded stadium. The wider the dish, the more of that faint signal you can corral into your microphone.
That's a great analogy.
Webb needed a mirror over 6 meters across to do this job.
But a solid 6-meter mirror is a logistical impossibility for spaceflight.
Right, because there's no rocket payload carrying on the planet wide enough to hold a single piece of glass that large. It simply would not fit inside the aerodynamic cone of a rocket.
Exactly. So they built it out of 18 separate hexagonal segments.
The origami fold.
Yes, the origami mirror. These segments had to be folded up for launch, packed into the rocket like incredibly complex origami, and then once it blasted into space, it had to unfold itself.
It just sounds so risky.
It was. Those 18 hexagonal mirrors had to swing into place and align in the freezing vacuum of space to within a fraction of the width of a human hair. They had to act as one perfectly smooth, 6-meter-across mirror.
The precision required is just difficult to wrap your head around. But I have to bring up one of my absolute favorite details from the sources here. The mirror isn't just regular silvered glass. It is coated in a whisper-thin layer of actual gold.
Yes, it is.
Why gold? I assume not just to make it look expensive.
No, not for aesthetic reasons at all. It's because of how gold interacts with light at the atomic level. Gold reflects infrared light exceptionally well. Normal mirrors, like the ones you find in a bathroom, are highly reflective for visible light, but they actually absorb a significant portion of infrared light.
Oh, I see. And when you are trying to capture a signal that has been traveling for 13 billion years, you absolutely cannot afford to have your own mirror absorb the data.
You need maximum efficiency. So the gold coating bounces roughly 99% of that precious infrared light directly into the sensors.
Let me just push back on the clean, sterile engineering aspect of this for a moment, because we really have to look at the human anxiety of this mission design. It is, frankly, terrifying.
It was a very stressful time.
Right, because Webb is 1.5 million kilometers away. It is far too distant for any astronauts to repair. When Hubble launched back in 1990 and they realized the mirror had a microscopic flaw, we had a safety net.
Right, we sent a space shuttle up.
Exactly. Astronauts did a spacewalk and they installed corrective optics. With Webb, there are no second chances.
None at all. The distance makes it completely unreachable.
That reality must have just dictated the entire 30-year development cycle. Because it had to unfold in space, there were hundreds of intricate steps.
There were. The deployment sequence was this massive chain of automated events. The tensioning layers of the sunshield had to pull tight one by one. Structural booms had to extend. Mirror segments swinging out on hinges and latching into place.
Yeah, it's just staggering. If a single cable snapped, or if one hinge froze in the cold, the entire machine could have become useless space debris.
The sheer terror of it cannot be overstated. Thousands of people dedicated their entire careers to this project, waiting 20 years. And then they just had to sit in a control room on Earth, watching telemetry numbers on a screen, hoping the automated sequence worked.
No manual override.
No manual override. But the gamble worked. The deployment was flawless.
The golden eye opened. Okay, so after all of that, decades of design, billions of dollars, the nerve-wracking weeks of unfolding, what has this golden eye actually bought us? Let's look at the payoff.
Well, the early scientific findings are already incredible. Let's start with the deep past, the infant universe. Webb has successfully spotted galaxies from just a few 100 million years after the Big Bang.
Which, in the timeline of a 13.8 billion-year-old universe, that is practically the morning after.
Exactly. But what's really fascinating is that these early galaxies look more numerous and much more developed than our cosmological models predicted they would be.
Oh, really? So our assumptions about how quickly the universe grew up were wrong.
They seem to be, yeah. The galaxies appear far more massive and structured than the timeline suggests they should be.
Some people might hear that and think, well, science is broken, we failed.
No. That is actually how science should work. Finding something that doesn't fit your model isn't a failure, it's the prize. It forces theorists back to the drawing board to ask better questions and build a more accurate theory.
That makes a lot of sense.
Yeah, Webb is disrupting our baseline understanding, which is exactly what you want it to do.
So that covers the deep past.
Yeah.
But reading the research papers on exoplanets, it shows Webb is doing things much closer to home that feel distinctly like science fiction.
Oh, absolutely. Exoplanet research is thrilling right now.
It is essentially looking at planets around other stars and acting like a remote chemistry lab.
That's a great way to put it. When a planet passes in front of its host star, from Webb's point of view, a tiny fraction of that starlight filters through the planet's atmosphere.
Okay, so the starlight shines through the alien air.
Yes. And different gases in that atmosphere absorb different, very specific wavelengths of that light. So by analyzing the light that finally reaches Webb, astronomers can see chemical fingerprints.
That is amazing. So Webb is sensitive enough to read these fingerprints and tell us what the air is made of on a world trillions of kilometers away.
It is. It has already detected things like carbon dioxide and water vapor in the atmospheres of distant exoplanets.
Which is laying the groundwork to potentially find hints of life out there.
Potentially, yes. It's an incredible capability.
I do have to ask a natural follow-up, though, and I'm sure you listening might be wondering this too. Does this mean the Hubble Space Telescope is totally obsolete now? Should we just turn it off?
Oh, no, not at all. That is the happy answer here. They are partners.
Oh, okay.
Yeah, Hubble sees visible and ultraviolet light, and Webb, as we've discussed, sees infrared. So they aren't competing.
Right, they're looking at different things.
Exactly. Together, they build a much fuller, richer portrait of the cosmos than either instrument could generate on its own.
It really is a remarkable synthesis of engineering and physics. I mean, wrapping this up, the James Webb Space Telescope operates as a time machine and a chemistry lab rolled into one.
It really does.
It's this massive gold-plated mirror sitting out in the deep cold, catching stretched light that has been traveling since the dawn of space and time. And it's just such a testament to human patience. People waiting 20 years to see if their life's work would pay off, just so we can understand the universe we came from.
It is a profound monument to long-term human commitment. And, it leads to a really fascinating final thought for everyone to mull over.
Oh. What's that?
Well, we've discussed how Webb looks at ancient galaxies and reads the chemical air of planets trillions of kilometers away. But consider this. What happens when an instrument this incredibly sensitive, powerful enough to see the dawn of time, points its golden eye at a patch of space we previously thought was completely, utterly empty? If we look deep enough into the absolute freezing dark, what unseen infrared empires might be hiding there, just waiting to completely rewrite our place in the cosmos all over again?
We built a machine to look into the past, only to realize the past has an entirely new future waiting for us to discover. Thank you so much for joining us on this deep dive. See you next time.